Bismillahirrahmanirrahim. Welcome, my dear students. This is module 2, lesson number 3, and today I will teach you the electronic configuration in an atom. So let's go to the lesson. Electronic configuration is simply the arrangement of electrons in an atom according to the energy level. Energy levels are actually the orbitals, the subshells. So these are arranged in the fashion according to 3 rules, and these rules will come step by step when I'll explain you. But now you learn that it is increasing according to the energy level, and I already told you in the principal quantum number, the number 1 is the lowest energy level, and number 2 is higher, number 3 is more higher, 4, 5, 6, and this 4th or the 7th is the highest energy level. But here we can reach up till the 4F. So you see here, this is the sequence, and the reasons of this sequence will come step by step according to the rule. But here you need to learn that S contains 2 electrons, P contains 6 electrons, B contains 10 electrons, and F contains 14. And when you write the configuration, the first these numbers and the letters. These numbers, this explain the principal quantum number n. This is 1, 2, 3, and up till this 4. And the second thing comes is the letter. This letter represents the angular momentum quantum number, that is L. And these are basically 4, S, P, D, F. Okay. And on the right side, in the superscript, there are number like 2, 6, 10, and 14. These are number of electrons, and this will change according to the atom we choose, like lithium, magnesium, beryllium. So this will change according to number of electrons. So there are 2 methods of writing electronic configuration. This is called long method of writing electronic configuration, and I'll teach you the short also. Wait some time. And the second method is orbital diagram. In this orbital diagram, you show the electrons in the box. The box represent the orbital, and the arrow represent the electron. This also I'll teach you in detail. So let's go to the rule step by step to learn this long form and the short form of the electronic configuration and the orbital diagram. So number 1 is the Abba principle. Abba principle states that electrons are filled in the orbital according to the energy level. And this is the diagrammatic representation of the level. 1s is lowest energy level, then 2s, then 2p, 3s, 3p, 4s, 3d, 4s, 4p, 5s, 4d. And this diagram is represented in another method. This is more simpler, and you might be familiar with this. So I am reading this according to the energy level. The first is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So these are written in the sequence in the energy level way. 1 is the lowest energy level, and the last one here is the 4f, but in the diagram it is 7p is the last highest energy level orbital. So this you have to draw this diagram to write this electronic configuration, or you memorize both way, whatever is easy for you. And for me, I will tell you that you learn how to draw this diagram first, so you can write this long electronic configuration easily. Memorizing might make mistakes. So number 2 rule is the Hund's rule. Hund's rule says that the most stable electronic configuration in the subshell is with the greatest number of parallel spin. So by example, I'll tell you, if the students have separate rooms, so they would like to live in separate rooms, not in the paired form. Similarly, the electrons want to live in separate orbitals with the parallel spin instead of living in the paired shape. So here, these are the example here: carbon, nitrogen, oxygen, fluorine, and neon. And this is the example of 7 electrons 7 electrons means here this is the nitrogen, 1s2, this 1s2 here, and this 2s2, this is here, and 2p3, these 2p3 electrons are unpaired electrons. This is called unpaired electron. So this 7 example, let me show you how to write this orbital diagram. Okay, this is important to write the orbital diagram because this will tell you this is paramagnetic or diamagnetic and how many unpaired electrons are there in the atom. So let's start with the carbon. So carbon have 6 electrons in the atom, and the long configuration will be like this: 1s2, 2s2 and 2p2. So total 6 electron, 2 plus 2 plus 2, these are 6 electron. And when we make the diagram, orbital diagram, so 1s2 will be like this box and 2 electrons will be in paired form. 2s2 also contain 2 electron, one clockwise, another anti-clockwise. Now 2p, there are 3p orbitals, 2px, 2py and 2pz. So let me draw this. This is 2px, this is 2py, and then 2pz. In the s, both s have 1s and 2s, it is single orbital. So let me write for you to remember. This is 2px, 2py and 2pz. Now we have 2 electrons, so this will come in the first orbital. The second electron will go in the second orbital. Instead of living in the pair, it will remain unpaired. So we have here 2 unpaired electrons. Unpaired electrons. And sometime when these electrons when get higher energy, so this also jumps to come in this orbital. So we can say this, so delete this electron, these electrons will jump here, this electron will jump from here to this 2p z. So now instead of 2 electrons, you can say you have 4 unpaired, sorry, this is unpaired electrons. So carbon in the ground state will have 2 unpaired electrons, and if this is 1 electron jump from this 2s to 2p, this will become 4 unpaired electrons. Okay, now we take the example of, after the carbon, it is nitrogen. So nitrogen have 7 electrons, so let us draw this nitrogen also. So nitrogen have 7 electrons, so this will be 1s2, 2s2 and 2p3, so total 7. Now I will not draw 1s2, I'll just draw 2s2 to save the time. You can draw all 2s2, and 2p will be 3 orbital, as I already told you. This is 2px, 2py and 2pz. So 3 electrons will remain unpaired and separate orbitals. So these are 3 electrons, so we can say here 3 unpaired electrons, 3 unpaired electrons. Now on the basis of unpaired electron, if you see the unpaired electrons, then atom will be paramagnetic. It is paramagnetic. I'll show you the details diagram in the next slide. So similarly here, if we go to the other atom, the oxygen, it will have 2 unpaired electrons, and fluorine will have 1 unpaired electron, and neon will have completely filled orbitals. All are paired, no unpaired electrons. So this will be diamagnetic. This will be diamagnetic because there is no unpaired electron. So let me draw this neon for you to understand more. So now I'll draw the neon with the 10 electrons. So neon, 10 electrons, configuration will be equal to 1s2, 2s2, 2p, 6, and you no need to draw 1s2, just draw 2s2. This is 2 electron, both paired, and 2p will have 3 orbitals, 2px, 2py, and 2pz. 6 electrons are here, so 1, 2 and 3. First electrons will try to remain separate, but if more electrons are there and orbitals are not enough, so then they will start pairing with each other. So this will be paired. This is 5th electron and this is 6th electron, so all paired. So we say no unpaired electron here. No unpaired electron. So if the electrons are unpaired, the atom will be paramagnetic. If there is no unpaired electron, then it will be diamagnetic. So let's see this in the diagram. So we answer quickly this answer. The carbon is paramagnetic. This is on ground state. If this electron jump here, then it will be 4 unpaired electron. Okay. Nitrogen is also paramagnetic because it have 3 unpaired electron. Oxygen is also paramagnetic because it have 2 unpaired electrons. Fluorine is little paramagnetic, but the neon is diamagnetic. There is no unpaired electron. So I hope you understand this Horn's rule and the paramagnetic and diamagnetic. So this is the detail here. If you read all this information, the reason is that when the electron have parallel spin, it becomes like little magnetic power. So they are attracted by the magnet. That's why it is called paramagnetic. Here you see this 2 electrons are unpaired, so they have parallel spin, so this becomes little bit magnetic. That's why paramagnetic. When there is no unpaired electrons, so they cancel each other, and it is not magnetic, it is repelled by the magnet, so it is called diamagnetic. Dia means no, diamagnetic. Okay, and it is represented by the magnets also. So the next rule is the Pauli exclusion principle. It says there's not possible that 2 electrons in the same atom can have 4 similar quantum number. So no 2 electrons in an atom can have the same set of 4 quantum numbers, because the electrons will live in the parallel spin. So when opposite spin, when they live in the opposite spin, then they are called paired. When they are paired, so one is plus half, that is spin quantum number, the other will be minus half spin quantum number, so the last quantum number will be different. So in an atom, no 2 electron can have all the 4 sets of same quantum numbers, because they will have opposite spin. So this is the meaning of paired spin, this is the meaning of unpaired spin, and each orbital can contain maximum 2 electrons. So that's why I taught you that the number of electrons will be always double to the number of orbital. Okay, now come to the exercise. This is the exercise. It is asking ground state configuration for the sulfur. So sulfur have 16 electrons. Let me write it 16 electrons here in sulfur. So we write the configuration: 1s 2, 2s 2, 2p6. This is, again let me remind you, this is K shell and this is L shell, both are complete. Then we go to the third shell, then it will be 3s2, so it become total 12 electron, and we have 16, so we go to 3p, will be 4 electron to make total 16 electron. So because sulfur have 16 electrons, if you make the total, this is 2, 8 and this 6, total 16 electron. So now when you make the block diagram, so this 3s, no need to make the block diagram of this inner shells, only the valence shell. So this is 3s, this is 2 electron, so this will be paired spin, 2 electrons both will come here. So 3p, I will draw here 3px, 3py and 3pz. This is 3px, 3py and this is 3pz. Let me write for you: 3px, 3py and 3pz. Total 4 electrons are here. So first electron comes here, it want to leave separately, second electron also separately, third electron also separately, but the fourth electron have no choice but to go and make a pair couple with the first electron. So there will be only 2 unpaired electrons. So we can say here answer 2 unpaired electrons in the sulfur. Unpaired electrons. Because of this 2 unpaired electron, it will be paramagnetic. Okay, so this will be paramagnetic. Okay, the palladium is a large atom. We will not do for the palladium. Come to the sulfur. So sulfur will have how many electrons? Sulfur have 15 electrons. So let me write the sulfur also. So sulfur is 15 electrons. So first you must see the number of electrons from the periodic table and then write the configuration. 1s2, 2s2, 2p6, this become 10. So let me show you, this is 2 electron, this shell is filled, and this is K, this will be L, both are complete. Then we go to the third shell, so 3s2 and 3p, I think 3, so 15 total, yeah, 3p3, so this is 2 here, 3p3, 15 electrons total. This information will be from the periodic table. So we will make the orbital diagram for 3s here. This orbital and 2 electrons are there, so they both will be paired, and the 3p same, 3p here, 3px, 3py and 3pz. 3 electrons are there, they are very lucky. All of them will remain separately with the parallel spin, and you can say here this have 3 unpaired electrons, 3 unpaired electrons, and because of this 3 unpaired electron, it is paramagnetic. So I hope you understand this, how to check how many unpaired electrons in the last shell, valence shell that is called, and on the basis of how many unpaired electrons are there, you can decide this is paramagnetic or diamagnetic. If you see there is one electron unpaired, then it is paramagnetic, any one or 2 or 3, and there is, if there is no unpaired electrons, all are parallel, then it will be diamagnetic. So the last thing is here the short method of writing the electronic configuration. So here to understand this, it is very easy. Instead of writing very long configuration, this is a method to make it short. So to this you have to understand the periodic table. You see here helium is completely noble gas, completely filled electrons, all shells are full. 1s2 is complete, then it comes here, second shell is filled, third, fourth, fifth and sixth, like this. These noble gases have all the electrons filled, means it is satisfied, octet rule is satisfied, so they will not have any unpaired electron, and we can use this as a short form for the writing the periodic table, writing the electronic configuration. See here, in the hydrogen 1s1, helium 1s2, this is complete. So instead, in the lithium, instead of writing the 1s2, we write helium here. So similarly, when we reach this neon, when the neon have 10 electron in the neon, so it means all the electrons are filled here. So now when the next sodium, instead of writing 1s2, 2s2, 2p6, we write just neon in the bracket, and in the last we say 3s1, so become 11. And then when we reach here with argon with the 18 electrons, so now instead of writing this complete configuration of 1s2, 2s2, 2p6, 3s2, 3p6, we just write the argon in the bracket. It means this is 18 electron, and the 19th electron will come outside the argon bracket, that will be 4s1. So then it becomes 36, then it is krypton. So instead of writing for 36 electronic configuration long, you just say krypton in the first bracket. So this krypton will represent the 36 electron, then you can write 5s1. So instead of writing long configuration, this is the short method. Just you see this diagram, this chart, this table will teach you that when you can use the next noble gas. So it will start from helium 2, neon 10 electron, argon 18 electron, krypton 36 electron. Like this way you can make a short electronic configuration. So main thing is here to learn this diagram, orbital diagram, and to check how many unpaired electron, and to decide which one is paramagnetic, which one is diamagnetic on the basis of unpaired electron or the paired electron. So I hope you understand this lesson today. It will be easy for you. This is the end of the module number 2. Okay, see you in the next module.